we're going to be again finishing up that rational function asymptotes homework that we had started last class. We're not going to do the homework at home. We're going to do it in class. And then we're going to do inverses of rational functions. I think I showed you my magic trick last class, actually, so that's already done. My bad. And then we want to get maybe into rational models and proportions. There's no class at all next week, so don't come at all next week. All right, working on that. And then I've opened up all the old, I believe I have. If I have not, check with me. I reopened all the old MyOpen math assignments over Thanksgiving, so people who have fallen behind on those can pick them up and do them and get those done, because people have not been getting those done. So Monday, we have that Intro to Rational Functions homework due that we're talking about, and then the following Monday, we'll have Simplifying Rational Expressions due, and as well as Units, Rates, and Proportions due. So we'll take a look at, we'll see how we get, but I may need to, after the end of today, we may just swap those two around and do them in different order. I might do this, since we did do the ratios and rates first, I might move those around a bit. Okay, so everybody grab out your Unit 6.
I think we were finishing because mine's complete.
We did the last page. You said the first page is going to be for review.
I'm sorry, what's that again?
We did this, the last page.
Oh, right.
And then you said this was
Yes, we didn't do the beginning. That's right. That's correct. Thank you so much. All right, let's put them on track here. Okay, so. So what we were looking at is asymptotes and translations. So asymptotes is kind of where we sort of left off. We did not do that first part because it was so close to what we've done already. So what I kind of wanted folks to do is take a look at this and figure out, have we done number one yet or not? Not yet? Okay, so these are not the basic one. Remember, the basic one starts off with 1 over x something. Right? So the basic one starts off with a 1 over x, and then you translate it by adding stuff here and adding stuff there. Yeah.
Which one?
We're doing this one. That one. So these are not that, because it has an x on top. Right? And this one over here has a 2x plus 1 on top. So these are not the basic one. These are just, so we're not looking at, at having you transform them. These ones we're doing that, stepping back more in the beginning, where you just look at it, and from the picture you tell what its domain is, what its range is. It's a vertical asymptote and it's horizontal asymptote. So those are the things that we're doing here. So let's take a look. Let's get right here. Actually, we'll move down a little bit more. So if we take a look at this first one, see if you can figure out, and I would say try to find the dotted lines first.
Yeah.
Right, so figure out where your dotted lines go. And that should kind of help you figure out what the domain is, what the range is, and what those asymptotes are. This dotted line is the asymptote. So take a few minutes and work on these, and then we'll come back and talk on them. But so does everyone see why I have a dotted line here? Yes, how it splits these two? That's the line that this doesn't touch this way, that one doesn't touch that way. Find the dotted line in this direction and draw it. And then that should help you figure out what the domain, the range, and again, these dotted lines are the asymptote that you're drawing. Do the same thing over here. Over the first one. So my asymptotes look like they're right along there. So what's my domain? X can be anything except for it can't be 2, correct? So X can't be 2. And then Y can be anything except for it can't be 1. So Y can't be 1. So then, what are the asymptotes? Well, the horizontal asymptote is this one right here. This, the horizontal means along the horizon, right? So horizontal is this one here. Vertical is this one here, up and down. So horizon, like the horizon, that's this one here. Where does it go through? It goes through what? 1. So it's the y equals 1. This one is the one that goes along with this one, y equals 1. Because remember, these folks match up. So that one matches up with this one, right? And then this one will match up with that one. So that one must be the x equals 2. Right? So if y can't equal 1, then y equals 1 is a line it can't touch. If x can't equal 2, then x equals 2 is a line that it can't touch. So everybody go ahead and finish up B. And then there's a couple more on the next page, I believe. C and D as well. And we can try to answer number 2. So take a look at these ones as well. Okay, so let's take a look at these ones. The next one over. Let's see. Let me draw my little dotted lines here. Can't be here. Can't be there. So, so my domain is x can be anything except for it can't be -1. So x can't be -1. And then my range, I look at what y can't be 2. Right, so again, this means everything, it can be everything else except for 2. It's all real numbers except for 2 when we write this can't equals. So then my vertical asymptote, let's see, vertical is the up and down. That occurs at -1. So something at -1, which one's at -1? Oh, x. So it must be x is equal to -1. So that's this line here. And this one here is at 2. So what's at 2? Oh, y is at 2. So when y is equal to 2, that's my horizontal asymptote. Again, horizon, horizontal goes along the horizon. This one, interesting. So my domain, as I go along here, there's nothing that x can't be. Does everyone sort of see this? There's no holes or anything where x can't be. So this is all real numbers. This is negative infinity to positive infinity. But my range, okay, so what's the smallest my y is along here? The lowest it ever goes? 1. What's the highest it goes? 2. So it's 1 to 2. Can it touch 1? That's how you always do the range, right? Can it ever touch 1? No. So it's gonna be a rounded bracket. Can it touch 2?
Yeah.
Yeah, it goes right through 2. So that's a square bracket.
I thought everything under counted on this, like negative infinity up.
Yeah.
That's
So
where
you
I'm
could look
kinda
at it.
confused.
You could look at it as negative infinity up,
Yeah.
and then, but then it has to be 2 to positive infinity as well. That's what you can't be. So wait, we're not talking about what you can't be.
Well, I thought it could be.
It
everything.
could, so you're saying it can be down here?
Yeah.
So if I go along this graph somewhere, I'm gonna be down here. Where along this graph do you think I'm gonna hit this spot?
No, I guess I'm kind of confused on what we're looking at, yeah.
So what you can't be is only if there's one spot you can't be.
Yeah.
Otherwise, we'll look at everything you can be. The domain is pretty much, it's all of this. And so maybe it's better for you to think of it this way. If that's messed up for you, then maybe you should look at, instead of look at the domain as being from negative infinity up to -1, unioned with -1 to positive infinity. Because that might work better for you if you think of it that way.
Yeah.
Because that's the same thing. Those are equivalent. And you can also look at the y's as being from -infinity up to 2, but not touching 2, unioned with 2 to infinity. So that kind of, or if that works better for you, the way you kind of look at it, then do it that way. The vertical asymptote, there is not a vertical asymptote. There's nothing here where it goes closer and closer and never touches, so this is none. Horizontal asymptote, there's totally one here though. Do you see where it gets closer and closer to it and never touches it? The asymptote is that thing, like, I'm not touching you, you're getting closer and closer to it, and you're not touching it. That's the asymptote. So we have one here. This is a horizontal one, right? So then what's it at? It's at 1. What is 1 along here? Is my x 1 or is my y 1 here?
Why?
My y is 1, so y equals 1. Stick with the next one. All right, so this one is kind of back to that familiar sort of stuff where I have my little x's, right? Or my little dashed lines here. But there's also this hole, don't forget that. So my domain is x can be, x can't be, what can x not be? Well, it can't be 1, but there's also this hole here, it also can't be -1, yep. So x can't be 1 or -1. Or if you like to do it the other way, Eric, you can also do it from, if I kind of go along this line, I go out to -infinity up to -1, and then I join that with -1 to, well, up to +1, and I join that with +1, this part here is +1 out to infinity.
So you're just sliding on the line to figure this, right? You're
Yeah,
just kind
I'm
of,
sliding along the x line to figure out, well, I'm
Well,
sliding along, I'm
the-
sliding along this line to
the
figure out
other
what
one.
my x's can be.
right, okay,
So my x can be -infinity up to that spot,
okay.
and then it hops over -1 and continues on down here. Then it kind of has to hop over 1 to get onto this side.
Okay.
And then my range, let's see, my range is going to be similar idea, right? I go from -infinity up to, has a hole here, at, what is that, maybe, it's at -1/2. So this is -infinity to -1/2. And then it goes up from -1/2 to 0. Wow, I didn't realize this was this complicated. And then it goes from, and then on this side over here, we go from 0 up to infinity. So yeah, I just slide along the lines of the furthest down to my highest up point. Right, so for the domain, I'm sliding along the x-axis to try to figure out where am I along my line as I go along the x-axis. And then for my range, I start off with the lowest I can be along my y-axis and slide along the line to figure out how to get up to the top. And I'm trying to go from here to the top along this line. So the range, you could also write the range as x can't be, what can it not be? It can't be -1/2, and it can't be 0. You can write it that way as well. Either way. I'll write that better. It seems a little bit messed up. Maybe I'll do it in a different color. Or I'll try to do it neater. X can't be -1/2 or 0. Yeah.
Isn't range supposed to be y?
Oh, I'm sorry, you're so right. It is supposed to be y.
And,
Thank you so much. Y can't be -1/2 to 0.
and
yeah.
for C, should domain have x can't equal a C in?
No, this one doesn't. There's nothing that X can't be. X can be anything.
Okay,
Yeah. There's no restrictions on X.
because, yeah, for D at first, I only got Y0.
I'm sorry?
For D, for the range,
Oh, see, so also Y can't be, it can't be this spot right here. See as it goes up, it can't be -1/2 either. There's two of them.
okay.
Yeah, I missed that first one too when I first looked at it. But my vertical asymptote, so my up and down asymptote happens where? At, where does this occur? On the number line.
The vertical is 1,
The vertical one at 1. So what's 1? My X or my Y?
X.
My X, so X equals 1. That's the first one. That's the vertical asymptote. X equals 1. What's the horizontal asymptote? Where does that occur at? 0. What equals 0? Y? Yep. Y equals 0. You could also find these domains kind of that old-fashioned way. Remember where we said, set this, this can't be equal. Remember, you can never, ever, ever do what? Two things you can never, ever do. One of them is what?
Divide by 0.
Divide by 0. What's the other thing you can never, ever do?
Square root of a negative number.
Square root of a negative number. So here, there's no square roots, but we are dividing by something with x in it. So we can never, ever, ever let this x plus 2, or x squared plus 1 equal 0. It cannot equal 0. So if I were to solve this, then I would say, okay, how do I solve this? I move to the 1 to the other side, so x squared equals -1. And then I try to square both sides, but you can't square the root of the negative number. So x can't equal the square root of -1, but that's imaginary. So there's nothing that x can't be. Does that sort of make sense? So this does not exist. Does not exist. So x can't be, whatever x can't be doesn't exist. So x can be anything. So it means there's no restrictions. X is from negative infinity to positive infinity. Right, that's my domain. Another way of looking at it is to say, well, x squared plus 1 can't be 0. Well, that would happen when x squared is -1. When is x squared ever -1? Just look at that for a second. When is x squared ever -1? When I square x, I get a positive. X squared can never be -1. Does that sort of make sense for folks? So x can never be negative. X squared can never be -1 because you can never square a number and get a negative number. So, so that's why there is no restrictions. It's all real numbers. On this one over here, we can look though and see, okay, x squared minus 1 equals 0. Add 1 to both sides. X squared equals 1. So if we square root both sides, we'll end up with x equals positive or -1. Right? So that's why x can't be -1 or positive 1. So my domain is x can't be -1 or 1, because if we did, then we'd get 0 underneath, and you can't divide by 0. Right? The whole world just blows up. So that's a good thing.
So that's a way to do it without, if you don't have the graph.
Right. That's what I do if you don't have a graph. You kind of look at it that way. Right? X squared minus 1 cannot equal 0. And solve for what that is. Okay. So, right. So yeah, in C we only had, so in here if you wanted to write, you could say it only has this kind of asymptote. That's the only asymptote. So we'll write down what kind of asymptote that is, whether it's horizontal or vertical. What is that one? Write it down in here. Write down what kind of, is it like the horizon, or is it vertical? Which one is it? Horizon. If you look at it along the horizon, it looks like this, right? Or is it vertical? Has anyone written that down already? Yes? No? If I walk around, you've written it down? This one's horizontal over, yeah, then write it down. All right, so we're done with that section. The next part is rational function.
Skip that.
Oh, we did that already last time, didn't we? Okay, we'll go back. This is all one problem. Everybody has one? Great. So we're going to take a look at rational function models. So starting here. Let's get a reader. Natalia, go ahead and read the introduction and the first. Just go ahead and read all this. Go ahead.
Rational functions can be used to represent a variety of real-world situations. In this collaborative, you will examine two rational models. Government and corporate entities often make decisions using cost-benefit models. These mathematical models estimate the cost of performing some task in terms of the percentage of the task completed. As an example, suppose that in a certain city, a lake has become polluted. The city wishes to assess the cost of removing the
Pollutants. Yeah.
pollutants. Their environmental analysts determine that the cost-benefit function.
Is this one right here? So the cost is going to be 120 times x over 100 minus x, where C is the cost in thousands of dollars to remove X percent of pollutants. So X is what is the percent of pollutants that you're removing from the lake. So ever been to Grand Lake, in Oakland?
Mm-hmm.
It's pretty disgusting, right?
Yeah.
That was always our thing. Like whenever you're rowing, you do not want to row on the Grand Lake because if you fall into that lake, it's just awful, right? Toxic. Okay, so removing the pollutants will cost a certain amount of money. Obviously, the larger percentage you remove, the bigger your x becomes up top. This number becomes larger, and actually, the bigger the x becomes down here, the smaller number you're dividing from, which makes that larger also. So, as we're going to see, this becomes quite large as your percentage becomes larger. So first, we're going to find and interpret the value of C for x is 20 and x is 80. So we'll do this one together. All right, so here, if x is 20, C of 20, what's my cost again? My cost was C of x equals 120x over 1 minus x, is that right?
106.
Or 100 minus x. Okay, like that?
Yeah.
Great. Okay, so let's put 20 in for x, and I will get 120 times 20 over 100 minus 20. You should be writing this down with me. Yeah? I'm going to bust out my calculator, as all of you are as well. All right, so what did folks get? What did you get for the numerator? 120 times 20.
2,400.
2,400. And then the denominator is 80. So if I divide those, I will get, well, the zeros will cancel out a little bit, and then 24 divided by 8 is 3, so that's 30. Okay, so that's my cost. It will cost $30,000 to remove what percent of the pollutants? What's my X? 20. So it'll cost $30,000 to remove 20% of the pollutants. Seems reasonable, right? $30,000. The lake will be 20% cleaner than it is now. Okay, that seems good. Everybody understand that concept? Okay, great. Now, let's do x equals 80. Everybody do x equals 80. Find it.